One atomic bomb can erase an entire city in seconds. I am not talking about a large explosion like conventional weapons. I am talking about a completely different kind of power. A power that comes from the very center of the atom itself. When the reaction begins, it happens so fast that human intuition cannot keep up with it. In a fraction of a microsecond, atoms begin to split apart. Energy bursts outward with unimaginable intensity. Temperatures rise hotter than the surface of the sun, and a shock wave expands faster than anything we normally experience on Earth. The surprising part is that all of this destruction comes from an incredibly small amount of matter. Only a few kilograms of nuclear material can release energy equal to tens of thousands of tons of explosives. When I first began studying these reactions during the war, they appeared to me as equations on a chalkboard, numbers inside theoretical physics. But the deeper I looked, the clearer it became that we were touching a force of nature unlike anything humanity had ever controlled before. So what exactly happens inside the atom that allows such a tiny piece of matter to unleash so much power? When I first arrived at Los Alamos during the war, the place did not look like the birthplace of the most powerful weapon ever created. It looked more like a quiet scientific outpost in the middle of the desert. There were simple wooden buildings, dusty roads, and chalkboards filled with equations instead of military plans. Scientists walked around carrying notebooks, arguing about physics, drinking coffee, and writing calculations that stretched across entire blackboards. But inside those buildings, something extraordinary was taking place. We were trying to understand how the nucleus of an atom could release more energy than any explosive humanity had ever known. At that time, I was a young physicist, excited by problems, fascinated by puzzles, and completely absorbed in the beauty of physics. Like many scientists working there, I did not arrive thinking about weapons or destruction. I arrived thinking about mathematics, particles, and the deep laws of nature. The project was secret, extremely secret, but the scientific challenge was irresistible. We were trying to solve a problem that had never been solved before. Could the energy hidden inside atoms be released fast enough to create an explosion? The project was called the Manhattan Project, and it brought together some of the most brilliant scientific minds in the world. Physicists, mathematicians, engineers, and chemists were gathered together in one place with a single objective: to understand nuclear fission and determine whether it could be turned into a weapon before anyone else managed to do it first. The fear at that time was very real. Many scientists believed that if Nazi Germany developed an atomic bomb first, the consequences for the world would be catastrophic. At Los Alamos, I worked in the theoretical division led by Hans Bethe, one of the most respected physicists of the time. Our job was not to build the bomb directly with machines and metal. Our job was to understand the physics behind it. That meant calculating how neutrons move through uranium, how often they collide with atomic nuclei, and how rapidly nuclear reactions could multiply once they began. These were not simple calculations. Every number mattered. A small mistake in the mathematics could mean the difference between a reaction that fades away and one that explodes with tremendous power. What fascinated me most was the strange nature of nuclear physics itself. In everyday life, explosions come from chemical reactions. Molecules rearrange themselves and release energy stored in chemical bonds. But the energy inside atomic nuclei is millions of times greater. That energy is locked inside the nucleus by forces that operate at scales far smaller than anything we normally experience. When those forces are disturbed in the right way, the nucleus can split apart and release enormous energy. The key discovery that made everything possible was nuclear fission. When a neutron strikes the nucleus of a heavy atom such as uranium-235, the nucleus can become unstable and split into two smaller nuclei. This splitting releases energy immediately, but it also releases additional neutrons. Those neutrons can travel through the material and strike other uranium nuclei, causing them to split as well. In other words, one reaction can trigger several more reactions. This idea may sound simple at first, but its implications are profound. If each fission event produces more neutrons than the one before it, the reactions multiply rapidly. Instead of a single event, you get a cascade. One reaction becomes two. Two becomes four. Four becomes 8. And within a very short time, the number of reactions grows enormously. Our task at Los Alamos was to determine whether this multiplication could occur fast enough to produce a massive explosion before the material blew itself apart. To answer that question, we studied neutron behavior in extraordinary detail. We calculated how far neutrons travel before colliding with another nucleus. We measured how likely those collisions were to cause additional fission events. We examined how the shape and density of the uranium affected the reaction. These calculations filled notebooks and chalkboards across the laboratory. Day after day, we refined the numbers, tested the models, and argued about the physics behind them. At the time, much of our work felt like pure science. Equations, probabilities, neutron paths, energy distributions. It was easy to become absorbed in the intellectual challenge, but slowly something became clear. If the calculations were correct, the energy released by a nuclear chain reaction would be unlike anything humanity had ever witnessed. A very small amount of matter could release energy equal to thousands of tons of conventional explosives. And once the reaction crossed a certain threshold, it would accelerate beyond any possibility of human control. To understand why the atomic bomb is so powerful, you first need to understand what happens inside the nucleus of an atom. Most people imagine atoms as tiny, solid particles, like microscopic balls of matter. In reality, atoms are mostly empty space. At the center, there is a very small nucleus made of protons and neutrons. And around that nucleus, electrons move in complex patterns. Almost all the mass of the atom is concentrated in that tiny nucleus. And hidden inside it is an enormous amount of energy. The nucleus is held together by a force called the strong nuclear force. This force acts over extremely short distances and binds protons and neutrons tightly together. Under normal conditions, the nucleus remains stable, but certain heavy atoms exist in a delicate balance. Uranium-235 is one of those atoms. Its nucleus is so large and complex that it can become unstable if disturbed in the right way. The disturbance comes from a neutron. A neutron is a neutral particle that can move easily through matter because it carries no electric charge. When a neutron approaches a uranium-235 nucleus and collides with it, the nucleus can absorb that neutron. This additional particle pushes the nucleus into an unstable configuration. The balance that was holding the nucleus together suddenly breaks. When that happens, the nucleus does not simply crack like a piece of glass. Instead, it stretches, deforms, and then splits into two smaller nuclei. These fragments move apart at tremendous speed. This process is called nuclear fission. The moment the nucleus splits, a large amount of energy is released. That energy appears as kinetic energy in the fragments and as radiation. But something else happens at the same moment. The splitting nucleus releases additional neutrons. Typically, 2 or 3 neutrons fly outward from the reaction. These neutrons travel through the surrounding material, and each of them has the potential to strike another uranium nucleus. If that happens, another fission event can occur. This is where the situation becomes extremely interesting. One neutron causes one fission event, but that event produces several new neutrons. Each of those neutrons can cause additional fission events. Suddenly, the number of reactions begins to multiply. Instead of one reaction, you get 2 or 3, then 6 or 9, then dozens, then hundreds, and very quickly, millions. This multiplication process is called a chain reaction. It is similar to a row of falling dominoes, but far more dramatic. Each event triggers several new events, and the total number grows at an astonishing rate. The entire process unfolds extremely quickly because neutrons move at very high speeds, and the distances between atoms are incredibly small. However, a chain reaction does not automatically become an explosion. Many of the neutrons produced in fission escape from the material without hitting another nucleus. If too many neutrons escape, the chain reaction slows down and eventually stops. For the reaction to continue and grow, enough neutrons must remain inside the material to trigger further fission events. This condition depends on several factors. The amount of fissile material is important because a larger mass gives neutrons more opportunities to collide with other nuclei. The density of the material also matters because closely packed atoms increase the chances of interaction. Even the shape of the material can influence whether neutrons remain inside long enough to sustain the reaction. When the conditions are just right, the chain reaction becomes self-sustaining. Physicists call this state critical. At this point, each generation of fission events produces exactly enough neutrons to maintain the reaction. If the number of neutrons grows beyond this balance, the reaction accelerates rapidly. Once that acceleration begins, the energy released increases enormously in an extremely short time. This is the fundamental physics behind nuclear energy and also behind the atomic bomb. The splitting of atomic nuclei releases energy, but the true power comes from the multiplication of reactions. A single neutron can start a cascade of events that grows faster and faster until an immense amount of nuclear energy is released almost instantly. To truly understand the terrifying power of an atomic bomb, you have to imagine what happens when the chain reaction no longer stays small and controlled, but begins to grow without restraint. Earlier I explained how a single neutron can strike a uranium nucleus and cause it to split, releasing energy and additional neutrons. Now imagine what happens if those newly released neutrons immediately collide with other uranium nuclei around them. Each of those collisions produces more fission events, and each of those events produces even more neutrons. The number of reactions does not grow slowly. It grows explosively. Think of it this way. One neutron enters the material and causes one fission event. That single event releases 2 or 3 neutrons. Those neutrons travel outward, and each of them can strike another uranium nucleus. Now you may have 3 fission events instead of 1. Each of those 3 events again releases 2 or 3 neutrons. Suddenly you have perhaps 9 new neutrons moving through the material. Those 9 neutrons trigger even more fission. The numbers keep multiplying. 1 becomes 3. 3 becomes 9. 9 becomes 27. And the growth continues faster and faster. What makes this process so dangerous is the incredible speed at which it occurs. Neutrons travel extremely fast, and the distance between atomic nuclei is incredibly small. When a chain reaction begins inside a dense piece of uranium or plutonium, each generation of reactions takes only a tiny fraction of a microsecond. In a very short time, millions, then billions, then trillions of atomic nuclei begin splitting apart almost simultaneously. When a nucleus splits, the fragments shoot away from each other with enormous kinetic energy. That kinetic energy becomes heat as the fragments collide with surrounding atoms. Within an instant, the temperature inside the material rises dramatically. The material begins to heat faster than any ordinary substance ever could. The energy released by each fission event is small on its own, but when billions of these events occur almost simultaneously, the total energy becomes extraordinary. As the energy builds, pressure inside the material rises rapidly. The heated atoms push outward with tremendous force. The solid metal that once held the uranium together suddenly behaves like an expanding gas of superheated particles. The expansion creates an intense shock wave that pushes violently outward. This shock wave is what ultimately becomes the destructive blast of the atomic explosion. But there is another factor that makes the situation even more extreme. The chain reaction itself accelerates as long as the material remains dense enough to keep neutrons trapped inside. When the material is assembled into a supercritical configuration, each generation of reactions produces more neutrons than the previous one. The reaction does not simply continue. It speeds up. The multiplication becomes so rapid that an enormous fraction of the material undergoes fission almost at the same moment. All of this happens in a time so short that the human mind struggles to visualize it. From the beginning of the chain reaction to the full release of energy takes only a few microseconds. That is less time than it takes light to travel a kilometer. Yet during that tiny interval, an amount of energy equivalent to thousands or even tens of thousands of tons of conventional explosives is released. The temperature at the center of the reaction rises to millions of degrees. Matter is heated so intensely that it becomes plasma, a glowing state of ionized particles. The expanding fireball forms almost instantly, pushing outward and compressing the surrounding air. This compression creates the massive shock wave that can level buildings kilometers away from the explosion. The frightening aspect of this process is that once the chain reaction passes a certain point, nothing can stop it. There is no switch that can be turned off, no mechanism that can slow the reactions down. The physics takes over completely. The neutrons continue colliding with nuclei. The reactions multiply uncontrollably, and the energy release grows until the material itself is blown apart by the force it has created. In ordinary explosions, the energy comes from chemical reactions, and those reactions occur comparatively slowly. In a nuclear explosion, the energy comes from the structure of the atomic nucleus itself. Because the forces inside the nucleus are so strong, the energy released during fission is millions of times greater than the energy released by chemical reactions. That difference is what makes nuclear weapons fundamentally different from any other explosive humanity has ever built. To truly grasp why the energy of an atomic bomb is so immense, you must look at one of the most famous equations in physics, an equation written decades before the bomb was ever built. Albert Einstein expressed it in a simple form: E equals mc squared. At first glance, it looks almost too simple to carry such enormous implications. But hidden inside that equation is a profound truth about the relationship between matter and energy. The letter E represents energy. The letter M represents mass. The letter C represents the speed of light, which is an extremely large number, about 300 million meters per second. When you square that number, the result becomes unimaginably large. What Einstein discovered is that mass and energy are not separate things. They are different forms of the same physical reality. A small amount of mass can be converted into energy. And when it does, the amount of energy produced is determined by multiplying that mass by the square of the speed of light. When physicists first encountered this equation, it was a revolutionary idea, but it seemed distant from practical use. No one knew how to convert mass directly into energy in any measurable quantity. Matter appeared stable and solid, something that simply existed without releasing its hidden energy. But the discovery of nuclear reactions changed that understanding completely. Inside the nucleus of an atom, protons and neutrons are bound together by extremely strong forces. When a heavy nucleus, such as uranium-235, splits during fission, the resulting fragments do not have exactly the same total mass as the original nucleus. A very small portion of the mass disappears. That missing mass has not vanished in the ordinary sense. Instead, it has been converted into energy, according to Einstein's equation. The amount of mass lost in a single fission event is tiny, far too small to notice on an everyday scale. But when you multiply that small mass by the square of the speed of light, the resulting energy becomes very large. Each time a nucleus splits, roughly 200 million electron volts of energy are released. On the scale of individual atoms, that amount of energy is enormous. Now imagine what happens when not just one nucleus splits, but billions upon billions of them. In a nuclear chain reaction, an enormous number of nuclei undergo fission almost simultaneously. The tiny amount of mass lost in each reaction adds together, and the total mass converted into energy becomes significant. Even if only a small fraction of the original material is converted, the resulting energy release can be extraordinary. To give you a sense of scale, consider a kilogram of uranium undergoing fission. If a portion of that mass is converted into energy, the total energy released can equal the explosive power of tens of thousands of tons of conventional explosives. This is why nuclear weapons possess such destructive capability. The energy does not come from chemical bonds or combustion. It comes directly from the conversion of matter into energy at the nuclear level. Another remarkable aspect of this process is how quickly the energy is released. In ordinary chemical explosions, the reaction spreads through the material over a measurable period of time. In a nuclear explosion, the reactions multiply so rapidly that the energy release occurs almost instantaneously. Within microseconds, the energy stored in the nuclei is unleashed, creating temperatures of millions of degrees and pressures powerful enough to generate a massive expanding fireball. The realization that such energy could be released from matter itself changed the way physicists viewed the universe. Matter was no longer just a passive substance occupying space. It was a concentrated form of energy waiting under the right conditions to be released. The nucleus of the atom, once thought to be an almost insignificant detail of atomic structure, turned out to contain forces and energies far beyond anything seen in chemical processes. During the early years of nuclear research, many scientists were fascinated by the intellectual beauty of these discoveries. The equations worked perfectly. The physics was elegant and precise. Yet when these principles were applied to a weapon, the consequences became far more serious. The same equation that revealed the deep unity between mass and energy also explained how a small piece of matter could unleash destruction on a scale that had never before been possible in human history. I often found it striking that an equation simple enough to write on a chalkboard could ultimately explain the enormous power of nuclear reactions. A few symbols, a few constants of nature, and suddenly you have the key to understanding why the energy inside the atom is so vast that even a tiny amount of mass can transform into a force capable of reshaping entire cities. When people think about the danger of the atomic bomb, they often imagine only the explosion. They picture a powerful blast, something similar to the largest conventional bomb ever built. But the truth is that the atomic bomb is dangerous for several reasons that go far beyond the initial blast itself. The physics inside the weapon creates multiple destructive effects that occur almost simultaneously, each one powerful enough to cause devastation on its own. The first factor is the sheer amount of energy released in an extremely short time. In ordinary explosives, the energy stored in chemical bonds is released as the molecules rearrange themselves. That process takes time. Even if it happens very quickly, In a nuclear explosion, the energy comes directly from the atomic nucleus. The chain reaction multiplies at such a rapid rate that a massive amount of energy is released within microseconds. Because the energy appears almost instantly, it creates a violent expansion of matter that generates an enormous shock wave. This shock wave is capable of flattening buildings, collapsing structures, and throwing debris across large distances. Air is suddenly compressed and pushed outward with tremendous force. The pressure front moves through the surrounding environment faster than anything people normally experience. When it reaches buildings and structures, it can shatter walls, break windows, and cause entire buildings to collapse. The blast alone can destroy a large urban area within seconds. The second factor is the intense heat produced by the explosion. During a nuclear detonation, the temperature at the center of the reaction rises to millions of degrees. This extreme heat forms a rapidly expanding fireball. The fireball emits a powerful burst of thermal radiation that spreads outward through the atmosphere. Objects exposed to this radiation can ignite almost instantly. Wood, fabric, and other combustible materials can burst into flames even at considerable distances from the center of the explosion. This thermal pulse can cause widespread fires across an entire city. Buildings damaged by the blast may catch fire simultaneously, creating large firestorms that spread rapidly through urban areas. In many historical cases, the fires that followed the explosion caused as much destruction as the blast itself. The heat from the fireball can also cause severe burns to people who are exposed to the radiation, even if they are far from the center of the explosion. The third factor that makes nuclear weapons especially dangerous is radiation. When nuclear fission occurs, it releases not only energy and heat, but also powerful forms of radiation. Gamma rays and neutrons are emitted during the reaction and travel outward from the explosion. These forms of radiation are invisible and can penetrate deep into living tissue. Exposure to intense radiation can damage cells and disrupt biological processes inside the human body. In severe cases, it can lead to radiation sickness, organ failure, and death. Unlike the blast and heat, which act immediately, the effects of radiation may appear hours or days after exposure. This delayed damage makes nuclear explosions particularly frightening because people who initially survive the blast may still suffer serious health consequences later. There is also the problem of radioactive fallout. When the explosion occurs, radioactive materials can be carried high into the atmosphere by the rising fireball. These materials eventually fall back to the ground over a wide area. Fallout can contaminate land, water, and food supplies. In regions affected by fallout, people may be exposed to radiation for extended periods of time. Another reason nuclear weapons are so dangerous is the scale of their destructive power. A single device can release energy equivalent to tens of thousands of tons of conventional explosives. In modern weapons, the energy can be even greater. This means that one bomb has the potential to devastate an entire city in a matter of moments. The combination of blast, heat, radiation, and fires can overwhelm any emergency response or infrastructure. What makes this even more troubling is that the destructive effects occur almost simultaneously. Within seconds, the blast wave spreads outward. The thermal radiation ignites fires, and radiation begins affecting everything in the surrounding environment. The physics that makes nuclear reactions possible also makes their destructive consequences extremely difficult to control once the reaction has begun. For scientists who studied nuclear reactions, these facts gradually became impossible to ignore. The same principles that revealed the extraordinary energy hidden inside the atom also revealed how dangerous that energy could be when released in an uncontrolled way. Understanding these mechanisms made it clear that nuclear weapons were fundamentally different from any other weapons humanity had ever created. They combined several forms of destruction into a single event, and the scale of that event was unlike anything seen before in human history. To understand the full meaning of nuclear weapons, you have to imagine their effects not just as a scientific reaction, but as an event that unfolds across an entire city in a matter of seconds. When a nuclear explosion occurs above an urban area, the energy released by the chain reaction spreads outward in several devastating forms at the same time. The blast wave, the thermal radiation, and the intense burst of nuclear radiation expand rapidly through the surrounding environment. Within moments, an entire landscape can be transformed. The first visible effect is the formation of the fireball. In the center of the explosion, the temperature rises to millions of degrees. Matter is heated so intensely that it becomes a glowing sphere of plasma. This fireball expands rapidly outward, heating the surrounding air and creating an enormous pressure difference between the center of the explosion and the environment around it. The air is pushed outward violently, forming the shock wave that travels through the city. As the shock wave moves outward, it compresses the air with tremendous force. Buildings closest to the center of the explosion experience pressures far greater than anything they were designed to withstand. Walls collapse. Roofs are torn away, and structures are shattered within seconds. Debris is thrown across streets, and entire blocks can be flattened almost instantly. Even at distances several kilometers away, the blast can still break windows, damage structures, and cause widespread destruction. At the same time, the thermal radiation from the fireball spreads outward in all directions. This intense flash of heat travels at the speed of light and reaches distant areas before the blast wave arrives. Materials exposed to this radiation absorb the heat rapidly. Wood, paper, and other combustible materials can ignite almost immediately. Clothing and skin exposed to the flash may experience severe burns. The sudden burst of heat can start thousands of fires across the city within moments. These fires can combine to create large firestorms. When many fires ignite simultaneously, they begin to feed on oxygen from the surrounding air. The rising hot air pulls in more oxygen from the outside, strengthening the flames and causing them to spread rapidly through urban areas. Entire neighborhoods can be engulfed in flames as fires merge together. The destruction caused by these firestorms can continue long after the initial explosion has ended. Another destructive element spreads invisibly through the environment. The nuclear reaction releases intense radiation at the moment of the explosion. Gamma rays and neutrons travel outward at extremely high speeds and can penetrate deep into living tissue. People exposed to high doses of radiation may not immediately understand what has happened, but the damage inside the body can already be severe. Cells and biological systems begin to break down, leading to serious illness or death in the hours and days that follow. Above the explosion, the rising fireball carries debris and radioactive material high into the atmosphere. As the fireball cools, it forms the characteristic mushroom-shaped cloud. Inside that cloud, particles of dust, soil, and radioactive fragments are lifted thousands of meters into the sky. Eventually, gravity pulls these particles back toward the ground. As they fall, they spread radioactive contamination across a wide area surrounding the explosion. This radioactive fallout can settle on buildings, roads, water supplies, and agricultural land. People who survive the initial blast may still face danger from the contamination that follows. Exposure to fallout can continue for hours or days depending on the weather and the movement of the cloud. In some regions, the contamination may remain in the environment for long periods of time. What makes nuclear destruction especially devastating is the speed and scale at which it unfolds. Within seconds, a city can experience a massive blast, an intense thermal flash, widespread fires, and dangerous radiation. Infrastructure collapses. Communication systems fail, and emergency services are overwhelmed. Hospitals, transportation networks, and public utilities may be destroyed or severely damaged, making recovery extremely difficult. From a scientific perspective, all of these effects are direct consequences of the enormous energy released during nuclear fission. The chain reaction converts a small amount of matter into an immense burst of energy, and that energy spreads through the environment in multiple destructive forms. What begins as a microscopic process inside atomic nuclei rapidly becomes an event that can transform an entire city in a single moment. I often found it remarkable that such immense consequences could originate from the behavior of particles so small they cannot be seen. The physics itself is elegant and precise, yet when that physics is applied in the form of a nuclear weapon, the results are overwhelming. A reaction that begins within the nucleus of an atom ultimately becomes a force capable of reshaping the landscape of an entire city. When the war ended and the immediate urgency of the project disappeared, many of us who had worked on nuclear physics began to reflect on what we had actually helped create. During the years of intense research, the focus had been almost entirely scientific. We were solving problems, calculating neutron behavior, studying nuclear reactions, and trying to understand whether the chain reaction could truly produce an explosion. The work demanded concentration and precision, and most of the time our attention was absorbed by equations and experiments. But once the world saw the real consequences of nuclear weapons, the meaning of those calculations became much more difficult to ignore. For many scientists, the original motivation had been fear. In the early years of the war, there was a strong belief that Nazi Germany might succeed in building an atomic weapon first. If that had happened, the balance of power in the world could have shifted dramatically. That possibility pushed many physicists to support the research. Even those who had never imagined themselves working on military technology. The reasoning seemed simple at the time. If such a weapon was possible, it was better to understand it before an enemy did. While we were working at Los Alamos, the environment was filled with urgency and secrecy. The project moved forward at remarkable speed. Physicists, engineers, and technicians were all working toward the same objective. And every breakthrough brought the possibility of a working device closer. At that stage, most discussions focused on whether the physics would work, whether the materials could be produced, and whether the chain reaction could be controlled long enough to create the necessary conditions for an explosion. When the first nuclear device was successfully tested in the desert, the scientific achievement was undeniable. The calculations had been correct. The chain reaction behaved as predicted, and the energy release confirmed what the equations had suggested for years. For physicists who had spent their lives studying the fundamental laws of nature, the moment demonstrated the extraordinary power hidden within atomic nuclei, but that realization also carried a weight that many people had not fully anticipated. Once nuclear weapons were used in war, the reality of their destructive capability became impossible to treat as an abstract concept. The same chain reaction we had studied on chalkboards had produced explosions capable of destroying entire cities. The physics that had once appeared as elegant theory now existed as a force that could reshape the world in an instant. For some scientists, this realization created a deep sense of responsibility about how such knowledge should be used in the future. Discussions began to emerge within the scientific community about the role of scientists in society. Physics had always been driven by curiosity and the desire to understand nature. But nuclear weapons revealed how scientific discoveries could influence global politics and human survival. Some scientists became advocates for international control of nuclear technology, believing that cooperation between nations was necessary to prevent future catastrophes. For me, the experience was complicated. I have always loved physics because of the excitement of discovery. Understanding how the universe works is one of the most satisfying intellectual experiences a person can have. When you solve a difficult problem or uncover a hidden pattern in nature, there is a sense of wonder that is difficult to describe. Yet the events surrounding nuclear weapons also showed that knowledge does not exist in isolation. Scientific discoveries become part of the world, and the world decides how they will be used. In the years that followed, many physicists continued studying nuclear science, but with a growing awareness of its implications. Nuclear energy could also be used for peaceful purposes, such as generating electricity or advancing medical research. The same physics that allowed nuclear weapons to exist also opened the door to technologies that could benefit society. The challenge became learning how to guide scientific progress responsibly. One lesson that remained clear was the extraordinary power hidden inside the atom. The nucleus, once thought to be a small and almost insignificant component of matter, turned out to contain energies capable of transforming the world. Understanding that power required decades of careful research and brilliant insight. But once humanity discovered how to release that energy, it became impossible to pretend that the knowledge would disappear. The story of nuclear weapons is therefore not only a story about physics, it is also a story about how human beings respond to knowledge. The equations that describe nuclear reactions are neutral. They simply express the laws of nature. What matters is how societies choose to apply that knowledge. The same understanding that revealed the immense energy inside the atom also reminds us that scientific discovery carries consequences far beyond the laboratory.